All right, now you're having too much fun. So basically, I'll start the next part, which is the filter design to IIR systems. But before that one, remember to fill those forms. Those are very important forms to fill that basically will be used for the future generations to get what they are basically entitled to when you or your the followers will be getting into the summer jobs. So filling those information that helps you next year and the rest of the engineering students beyond. Okay, so let's see, does this one work? No, it doesn't. So IIR filters. So basically now we are talking about infinite impulse response systems, which means that the filter always have somewhat linear, non-linear phase. So it's never linear phase filter. So basically, if you need a linear phase response, then basically the only way to get it is FIR, which has its limitations. But anyways, however, these are basically better amplitude response with lower number of calculations. So those, in that sense, it's more effective if you are interested only on the amplitude response. For example, on audio. Audio is excellent example where you almost never use any FIR filters unless it's a special need. For example, of course, sampling of the that easiest to do with the FIR, but otherwise you would do it with the IIR systems for several reasons. But anyway, so and then whenever you need high Q factor, meaning narrow bandwidth the filters, then the IIR is your answer. I should actually show a couple of things why that is on the white screen there. Good. So the black. Remember the complex unit circle. When you have a FIR filters, the only way to actually control the system amplitude response is with the zeros. When you put the zeros on the unit circle, you will get also the 0 points on the amplitude response like that. And then basically if you put the zeros close to unit circle but not exactly, you basically can do a kind of attenuation on passband to make it flat. So that could be, no, that's not correct. Let's put one more. No, it could be closer. Anyway, so basically you are putting some zeros to push the amplitude response and some points the down. Okay, and that's the only way to get it, and you still kind of get quite a lot of the stop and the feed through. Anyways, when you're taking a the opposite way on the pass band, you can still have the same stop band notches there, but for example put only a couple of these poles close to the unit circle, so basically you get more gain, but at the same way you get, say, better stop band attenuation. with fewer calculation points. It's just quite obvious when you're taking a look at this, since every one of these actually requires one multiply accumulation. It's basically the same as, you know, a number of zeros and poles is the same as the number of calculations plus one. Okay. So better efficacy with the less calculations. That's the IIR, why we are using IIR filters. All right. So back to this one. So the only kind of fallback on the IIR filter design is that these design methods are quite complex. There's only one design you can do by pen and paper. The rest of the design methods actually require at least some tables, transformation tables. But anyways, those are the four most common methods. So there's the digital filters, actually the first digital filters on the IIR digital filter were based on analog counterparts. So those are the classical analog filters like Butterworth, Chebyshev, elliptic, which probably you haven't heard of them. Okay, but there are some analog filters based on negative feedback and some let's see, Sallen-Key structures on operational amplifier circuits. Okay, and there you can make it kind of sample the system. Where you have an analog system, you can always make a model of the analog system, and bilinear transformation is one method of making a such kind of transformation. And where basically if you have an analog system, let's move it back here. There we go. So on analog system you don't have the C plane, but you have S plane. Okay, that's the S plane. This is the where the poles should be. That's the stable region, and this is unstable. Here the same things on the sampled system. You have stable region and unstable. So, and there, while the digital frequencies are on the unit circle, then this on S plane, these analog frequencies are actually on the J dimension. So that's where the J omega is. Here we had the point E to J omega. Okay, digital frequency. Stable, and there we have the system, for example, like that. That will be Butterworth design. Yep, I know it. Okay, basically this bilinear transformation is the way to transform these pole locations which are on the analog domain certain way that they actually fit into the this Z plane, and there's only a simple trick with you have a H of S. You basically move that one to H of S equals 2. I think it was 2 over T. Let's see. Oops. 2 over TS, yes. Just a calculation, 2 over TS. Z minus 1. Z plus 1. Okay. So actually, when you look at this one, you can kind of think of what is the frequency when Z is minus 1. The analog frequency would be either minus or plus infinity. So in one sense you take this j omega axis from infinity and minus infinity and turn it into the unit circle. Okay. Long arms. Yeah. And the basically it maps these frequencies here. If you have somewhat linear scale here, it will map that one in very unlinear manner on the this unit circle. Okay, but it's straightforward substitution of oops like that to get the transfer function from analog transfer function to digital. And it actually works with any system which has an analog transfer function, any continuous time system, pendulums or motors or whatever you have. You just bilinear transform that one and you have the digital model of the system. Okay. And yes, if you have a first order system on analog domain, then you get also first order system on digital domain. It doesn't affect on the amount of those zeros and poles. Well, poles yes, but zeros no. No, the other way around. It adds some zeros. So the order number doesn't change, but it warps the frequency scale quite drastically. Anyhow, if we have a say natural system, usually the order numbers are quite small on real natural system, up to say 8 or something like that. So you get easily a IIR system out of by using the bilinear transformation. Simple, effective, warps the frequency space. All right, that's one way to basically do the trick. The second one is kind of, it has a fancy name, it's parametric modeling. All right, so any dynamic system you can actually write a differential equation that describes the behavior of the system. Your physics teacher will tell you more if you ask, and he'll be very surprised that you asked. Okay. But anyways, that's basically quite simple. On this, well, that's the first method. The second method here. Parametric modeling. So we have, for example, second order. Well, let's see, ax dot dot plus bx dot plus cx plus some factor, or actually that is usually like that, is 0. That's a differential equation of second order showing, for example, how pendulum swings. Okay, that could be just, well, that's basically acceleration, that's speed, that's a local position. Okay, then those parameters just change, and that's the time derivative dx over dt, and that's squared, or d squared, so second time derivative. But anyways, there's also this parametric modeling, quite simple. You just replace dx over dt by delta x over delta t. All right, so it's simple sampling without any worries about the consequences. And delta x is just xn minus xn minus 1, so it's just a difference between two subsequent numbers, and this is, well, TS, sampling time. Simple linear interpolation of the difference equation. Depending on the sample time, if the sample time is short enough and the system hasn't changed much in between those time steps, then this is just fine. Okay, however, the problem of that one is, while the good point is that the frequency scale is actually still linear, it's still exactly those time points, it's just sampled time points. But the problem actually comes on the fact that, okay, let's see where I'm looking for, there we go. Think of the frequency space. On continuum time space, we have, for example, this system frequency response is something like that. It continues from minus infinity to infinity. Okay, but when we sample the system, what happens to that part of the spectrum? It aliases. We do the same aliasing error as we did on the very first lecture. So basically, this one aliases here, and you get the aliased spectrum at the top of this one. Okay, if we have fast enough sampling rate compared to this possible signal changes, it means that this is negligible. Okay, and then it works since there's nothing to alias. All right. Third method. Yes.
Possible to just create that with the really high sampling frequency first, and
yep.
then you have discretized it and you filter it again.
Yes. Yes. Decimate it.
Yeah.
Drop the do some digital filtering and stuff like that, and drop the sampling rate. The same as the this sigma delta A to D converter is actually doing. It's 1-bit conversion at the beginning. This A to D conversion for audio. All right. And then third one, direct design. It takes some balls to do it. Okay. So this would be direct design, meaning that you just start putting the zeros and poles on the positions you think they would be from the first place. Then you start twiggling these parameters a little bit to match exactly what's supposed to be the your filter design. Okay, not recommended unless you are doing just one single simple design, which is back actually the I think we have that one also on the exercise. So you can do the direct design only on one filter, and good luck with the other ones. If we put a 0 here on that omega 0 angular frequency, it means that it basically on that frequency we have 0 or infinite attenuation. All right. And complex conjugate pair, of course. And then we basically just take the these poles and put them close range at the same angle, meaning that we are also bringing some magnification or amplification of the signal here on the same frequency. So originally the system would be FIR and look like this. But we take the poles from the origin and push them nearby. Basically what it does, it makes the other part of this amplitude response more or less flat. Okay. And even this width of the filter can be adjusted quite easily. Well, half width. Half width is exactly the same as that one. The distance to the unit circle. Okay, how come? Oh. If we are here, remember the amplitude response? It's basically the product of e to j omega to 0 point times e to j omega minus 0.001, okay, divided by e to j omega minus pole 0 times e to j omega minus pole 1. All right. If you are somewhere in here, in far away location, basically all of these distances are just about the same. So distance from, for example, from here to there and there, it's about the same as, well, distances here and here are the same, as well as those distances about same. So if we are far away, then it's almost unity gain. And when we are getting closer, let's expand it a little bit. Okay, that's the unit circle, pole 0, that's the angle omega. All right, and that was the distance A. Think of the distance A here. This point here is basically the same as that one. Right. Well, yes. That distance. So this is same as that one. That's about the square, and magically this distance, when you're thinking again these two, it's about square root of 2 times A. So in here we have that distance is square, well, that one is about A, and this distance is square root 2 times A, meaning it's 1 over square root of 2, which is minus 3 dB. Okay. So basically this distance is roughly the same as the half width of the stop band. There, simple. And that's the only filter, IIR filter, I recommend anyone to design by hand. But then there's also this fourth method, optimized methods. Now we are talking about something that someone has already done for us, and it's there are plenty of research done on this field because there's a big need for IIR filter design. Okay, meaning that there are already tools to do optimized filters. Some of them are actually commercial, but well, MATLAB has most of the say non-commercial. You just need to have that expensive license from MATLAB. Or Octave also have some of these methods already there, even the optimized ones. All right, and that's the bandstop notch. The classical filters. I mentioned the classical filters on this bilinear transformation. Fundamentally, classical filters are well, those three filters are the most used filters. There's also the fourth one, which is Bessel filter. Well, it's nearly linear phase response, but when you do the bilinear transformation, it's nothing like that anymore. So only those three filters are actually recommended for, say, any use for the starting point. So fundamentally, the Butterworth, that's maximally flat passband, meaning that it's basically unity gain, and say quite simple to design. Then the second one, well, yeah, that was the let's see, blue, yes, blue line there, Butterworth filter, and that's what happens when you do the bilinear transformation to the analog filter. Okay. Chebyshev type 1 actually means that it has equal ripple on passband and high attenuation on stopband. There's also Chebyshev type 2, but those are not practical on analog filters, so basically it's no use to transform those to digital domain either. But anyways, the Chebyshev 1, which is the green, has a, say, it's quite fast response and goes very deep into the on the stop and attenuation. Okay, but now again, if we now make a deal, it's about the same deals what we did with the FIR filters. It's always you can control, or you can have either very good passband. If you allow some ripple, you get steeper filters. If you then allow some lower level of attenuation, then you again can squeeze the transition bandwidth shorter. So that's what happens on elliptic. So basically that's equal ripple on passband and stopband. Okay, and yeah, that's the history. So it's yeah.
So what does the equal mean? Equal ripple,
Equal ripple means a uniform ripple within the say +2 dB on passband, and then you know the stopband attenuation level. In that case, -60. Yeah, yeah, peaks at the same level. Yes. Right. So I already mentioned this one on the phases. So zero phase filter. That's just a one reminder that okay, if you really need to have the zero phase response, there is a way. So even with this nonlinear phase response filter, you can get a zero phase response by basically filtering the signal twice, you know, first on forward direction, then on backward direction. And of course, only for post-processing. It's hard to reverse the time in real life. Believe me, I'm old enough to know it. I have tried and failed. Okay. But, yeah. For some reason, I also put some funny filters here. This is a kind of filter you can sometimes use even with, say, audio data. Median filter. It's basically you calculate instead of calculating the average, for example, or something like running average or weighted average, like in FIR, you basically calculate the median. So that's the center value of the sample. Okay, good example. So you calculate basically the center value of some region here and replace the rest of the signal with that one. So median filter basically is some sort of low pass filter, very nonlinear. The good thing actually about the median filter, and that's the reason why it's used so widely, if you have a sudden peak there, it disappears. You take median of, well, values like 1, 2, 3, 100, 4, 5, 6, 7. The median would be 5. 100 doesn't affect. Okay, the same thing for average. 113 divided by 8. So it's 20 some, around 20. Average would be around 20, but the median is just 5. So running average actually would do a bump here, while the median filter goes just like that. So if you have a speckle kind of noise in your data, that's your filter, meaning astronomy or 2D. Dead pixels. Cameras has dead pixels. If you bigger the cell is, more probably it is you have a dead pixel there. How to get rid of that dead pixel? That's how you do it. Let's see, I have that one correct. So basically, the red dot there is that dead pixel, and basically we calculate the 3 by 3 median, which would be gray cell here. So that's the most frequent value. Right, and replace it. Ta-da, gone forever. All right. So that was the median filter. Matched filter, it's actually also kind of special filter used with all kinds of measurements. Basically, the idea is quite simple. If you know what you're looking for example, an echo of something, for example, echo cancellation on phone lines, right? You know what you are transmitting, so you can make actually a filter based on that one, or inverse filter based on that one, and remove anything that is reflected back. Okay, so fundamentally that's quite straightforward kind of thing. Or a radar, or acoustic radar, or that one. You measure snap, and then you can make a exact filter that passes only those frequencies through the system as you know they are. Anything else would be noise or artifacts. So that's the way to filter just this signal what you want to filter. Right. Woo! That was the theory part. About the exercise, I'll go through some of these with you, but anyways, let me. Okay, so now back to the exercise. Exercise 5, the first, we go and do the direct design by putting these notches. Make a bandstop notch filter with certain sampling rate, and basically to reduce, for example, line humming on your data. And yeah, impulse responses, that kind of things. Then basically the fourth one, I think this is quite close to the FIR, the exercise. Exactly, but now you need to design an IIR filter. Hey, wait a minute. Yeah, let's compare it with the your FIR design. Then again, you design, actually first try to parameterize your filter properties basically on the FIR exercise, and then design an IIR high pass filter with the basically same property. Oh no, that was the what I'm talking about. So IIR band high pass filter. This is just a design. So low pass, high pass. Yeah, okay. Then IIR filter, same as on the FIR filter. Comparison. Then again, same. I think did you already have this one? The 3-band equalizer on FIR. I don't remember. Well, but anyways, there's a kind of design, a equalizer, 3-band equalizer, very small, very basic one, meaning the tone control with us the discant and bass, or treble and bass. It also has a middle. Did it? No, okay. Yeah. Maybe I should actually draw you a graph what I'm looking for on this 9th exercise. Yes. Cam. Okay, it fits here. 5.9. Human ear, 20 kilohertz, the maximum frequency. And then basically the normally, if you put this one on bass, middle, and treble or discant, whatever that is called, depending on the continent, you basically have 3 different filters there. The bass filter is a low pass filter, the treble or discant is the high pass filter, and the band pass actually is more for middle. And the tone adjustment is very simple. You just add some gain to those bands and mix. So basically the system looks like this. There. Ta-da. So 3 systems, the outputs are just summed together. Or if you have same order system, you can sum the filters, coefficients, do the calculations only once. Okay, but now I should show you something with the MATLAB. All right. Some graph windows, just let me close the graph windows. There we go. So IIR filter design, and we start with this notch, dot, stop, and filter. Stop and bend. And a couple of parameters, for example, on say measurement systems, we could have a sampling rate only something like 1 kilohertz. For example, 1,200 samples per second. So this would be some measuring systems. Okay, and we have the line humming there. At which frequency? What is the most distinct one? The frequency there? No.
100.
Yes. Yeah, double the yes, double the 50 hertz. The rectifier actually does it. In here, it's the light rectifier basically which does it. There's no negative light coming out. Have you noticed? The negative cycle still have the positive light, so it's rectified. Okay. Anyhow, so we have the this noise frequency is 100 hertz. That's common in Europe. Line humming. There. Of course, nowadays we also have all sorts of other humming sources with higher frequency because of the switch power supplies. Okay, but there we have the sampling rate and we have the FN. We can now start designing the filter. Right. So basically, the corresponding frequency for this line humming is 100 hertz divided by 1200, or actually, let's do it like this: Fn divided by Fs times 2 times pi. That's the angular frequency of 100 hertz. And at this frequency we have notch, meaning the zero on unit circle. So z equals exponential of omega n times, well, j of course, and then the actually times j and minus j. So that gives us complex conjugate pair of zeros which are exactly the unit circle. So z plane of zz. There we go. So we have the 100 hertz signal is right there, I believe. Yes. Okay. Now we need. Yes. Yes. I and j actually imaginary units here. You can always overwrite both of them if you want to, so, which is fairly simple to do by using single letter variables. Okay, you can overwrite functions. You can overwrite exponential, for example. So, well, it gives.
Engineers like to use the J and I.
Yeah. J is for engineers, I is for physicists. Okay. I or J, who cares? Okay, so now we have the zeros at the right place, and let's take a quick look at the system parameters. So system coefficients for this one would be polynomial divided by these zeros. So these are the system coefficients. And now we can actually calculate the also the frequency response of this one, just to make sure that we have everything at correct place. Yes, exactly at 100 Hertz we have a lot of attenuation. Unfortunately, also the rest of the amplitude response looks a little bit bad. So it has some gain on the on higher frequencies, and then, well, it's just ugly. But it reduces the line humming. All right, then let's take a design parameters for that A, meaning the half width of the filter. For example, half width of the filter could be 20 Hertz. Enough notch. So the corresponding angle is there. And that's the same as the distance of pole to the unit circle. Pole equals to 1 minus omega hw times the exponential of something, but we already have it. It's on the same angle, so we just multiply it. It's basically just the distance changes. There, poles, and the let's see the z plane again. There, those are the zeros and pole locations. Ooh, and then the filter coefficients, polynomial defined by pole locations, and finally, oops. There we go. Nice design. Almost unity gain. That's close enough for me. And there, basically, let's take a quick look at. I would say it's about 20 dB. I should take this one out somehow. Plots, not plots, figure. Oh, there are the tools. There we have. Seeing is believing, so 20 dB, minus 20 dB and plus 20 dB, so it's about minus 3 dB point here and here. So yes, we have the notch filter, subband notch filter as designed. Okay, just two parameters. One, where's the notch, and then another one, how wide is the filter. Oops. There. Then the hard part. Different filters or these digital filters. I would start with say this classical filter design. There's nothing wrong with classical filters. And these are basically analog and then by linear transformation. And let's take a look at the document of butter, for example. Ooh, that's good. So basically we just need to give it the order number and the cutoff frequency as normalized cutoff frequency, and here the normalized cutoff frequency actually means times pi. Okay, meaning that basically the scaling factor or the cutoff frequency and the real cutoff frequency. Okay, I'll give you an example. So let's see. B U dot AAU ABU. Okay, there. Order number, for example, fourth order. WN is the normalized cutoff frequency, and in here, for example, 100 Hertz, and you divide that one by Nyquist frequency. That should give the cutoff frequency at the right place, but we'll see. So this is the filter design, simple like that. Let's make this not C plane. Frequency response, BBU, ABU. Yep. That's the fourth order Butterworth filter. It has fairly flat passband and then not too steep transition band, and the cut frequency is right here. Okay. Okay, if we had a design that we have to have the attenuation at 300 Hertz, at least 60 dB, then there's also a function but_ord to call to find out the whoops, lots of stuff here. Calculate the order number for the filter. Oh, that's nice. It also has the reaches the lowest order n of the digital Butterworth filter, but with no more than RPDB on pass band rip. Well, okay, that's mathematicians think that there is a ripple on Butterworth filter. It doesn't have ripple. It's rippleless filter. Okay. But anyways, I think that one defines the design point. Okay, those values there are passband, stop band, passband ripple, meaning in this case it's actually the no ripple, and stop band ripple. So it finds the n that fits into this box. Let's try it. So all right, so BBU, oops, not that one, NWN equals but_ord there. passband starts at, oh, so that was the 100 hertz, right? Did I put 100 hertz on that? Maybe. Okay, divided by fs divided by 2 there. Okay. Stop band, for example, at 300 hertz. Decibels 3 dB in here, and stop band attenuations, for example, 60 dB. Sixth order, and then that's the design cutoff frequency for that one. Yep. Yes, 60 dB at 300 hertz, and then yeah, the 3 dB point is at 100 hertz. Okay. Basically, you can do the similar kind of designs also with the Chebyshev one and the elliptic. They all have the similar helping functions. So let's see, but odd, Cheb 1 odd. Yeah, there. One odd would be used with the Chebyshev one filter design subroutine. Okay, an elliptic also. You can play with those. Then there's also, let's see, what else do we have here? There's also nice package on these computers. Basically, you can also, if you want to, you can use some of these design subroutines. Design filter designs any filter, IIR, FIR. You just need to give it parameters, and it does everything for you. Then I will also show you, although I know that some of you are working with the Octave, which does not necessarily have all the functions. It had the Chebyshev bezel butterword, so this exercise definitely can be done with the also Octave. But since we have this very expensive MATLAB, we also have very expensive tools like FDA tool. Did you know? Oops. Let me see if this one shows up. Okay, desktop. Alrighty, that's how you design a filter. So low pass filter, for example, let's make it IIR maximally flat, for example, and then we just make here the sampling rate, oops, cutoff frequency 100 hertz, design filter. Things for a while, and then you get this kind of maximally flat filter, or, well, there are all sorts of nice filters that you can actually play with. And okay, different order numbers. What does it do? And yeah, so that's a perfect tool to play with and design filters. It's not required though, since all of these exercises should be also be able to be done with the Octave or other, say, similar packages. But since we have the MATLAB, well, use the tools. One tiny hint on using this one, how to get these parameters, since I want also to, you know, some of these pictures there. If you want to, let's see, export. Well, where is the export, was it export? Okay, there. Clicking export, you can get the coefficients of these filters to the MATLAB workspace. All right, but actually right now it goes there as the second order system matrix. We haven't gone through that one yet. It will be on the next week. But anyways, you can get the parameters. You can take a look at the parameters here. Zeros and poles, step response, impulse response, group delay. Everything is here. So why I'm showing you this one now? Well, just because. I'm evil. All right, but
does MATLAB have any built-in optimization tool that you can just show that I want these parameters for my filter and compute it for me?
Yeah, well, you just basically can build it here. It's just, you know, click the correct parameters here and you get whatever you wish to. Yep. All right, so that's my part of the show. Have fun.